Okay, when you were a little girl, what did you want to be when you grew up?
I wanted to go into technical theater, actually.
What is that?
So that's like sets and light design and things like that. So the first circuits I built were actually for lighting for the theater.
Do you find it curious that you're now using lighting and sound in your research so many years later?
Yeah, I find it really curious. I think it's probably not a coincidence.
Right? Yeah, no, I love that. Welcome to Holy Shift, Biomedical Breakthrough Shaping Tomorrow. What is biomedical engineering exactly? It's about engineering solutions that improve human health, from new medical imaging tools to personalized cancer treatments. Holy Shift reveals the people, passion, and purpose powering the future of biomedical research. Today on Holy Shift, we are excited to welcome Dr. Annabelle Singer, the McCamish Foundation Early Career Professor in the Culture Department of Biomedical Engineering at Georgia Tech and Emory. She is trying to solve a long-standing, deeply human question we all have. Where do memories come from? Annabelle is trying to understand how brain cells communicate with each other to create and store the memories that are essential to our identities, and how to fix that process when it goes wrong in diseases like Alzheimer's. She has traveled extensively around the world and brings those broad perspectives into the way she runs her lab and thinks about her science. This is sure to be a fascinating discussion. Let's get started. Alrighty, well, good morning. Thank you for joining us at Emory University. And why don't you first tell us who you are and where you do research?
Yes, I am Annabelle Singer. I am the McCamish Foundation Early Career Professor of Biomedical Engineering. My lab is based at Georgia Tech, but I am both a faculty member at Georgia Tech and Emory.
Amazing. Okay, let's get started. You ready?
Yes.
If you had to explain your research at a dinner party, how would you describe it in one or two sentences?
Yeah. We're trying to create new brain stimulation approaches to Alzheimer's disease. If you think about the brain as an electrical circuit, a lot of the previous research in Alzheimer's has been on basically the biochemistry of the brain.
So biochemistry being more of the chemical components that happen? Okay.
Exactly. Things like that leads to new drugs.
Okay.
But if we think about it electrically, we can manipulate those electrical signals as well. And that's a new approach that we're trying to take.
Okay. So for someone who is thinking, what is a circuit? What is electrically? What does that look like? Like, how are you testing those pieces, or how are you digging into that versus the chemical component?
Yeah. So it started with technology called optogenetics, which allows us to shine light on particular neurons and make them fire these electrical signals. So that's how they communicate with each other. That technology is not quite ready for human use, but that allowed us to discover what frequencies of stimulation are really helpful in the disease. And then we discovered that we could actually achieve similar effects using sensory stimulation. That's literally lights and sounds turning on and off, but with millisecond precision. And with that, doing the right frequency, we were able to reduce pathology or some of the damaging parts of Alzheimer's.
So this is the part that's so fun and also complicated, because when you think of frequency, right, it's the wavelength, right, and how high or how low the wavelength is in it. And I think about the optical. You said optical genetics. So does that or genomics?
Optogenetics.
Optogenetics. Did I say that correctly? I love this. This is fun. Science is amazing. So really then, by seeing the way that light or different sensory things impacted the brain cells, you were able to identify some potential new ways to treat it that do not involve chemicals that we think of in the pharma industry for drugs. Is that accurate?
That's exactly it. Yes.
Love it. Okay. So you've already kind of hinted to this, but my question was going to be, what problem in the real world are you trying to solve? And I know you mentioned Alzheimer's. So can you tell me, was it something about Alzheimer's that you were personally passionate about, or how did you get into that disease specialty?
Yes. So I started in my graduate work studying neural circuits important for memory. And when I was there, that was at UCSF, University of California, San Francisco. when I was there, I was really lucky to get to visit the Memory and Aging Center there. They were really kind. They allowed me to shadow how they diagnosed and treated patients. And one of the things that I remember from that is I spent a whole day basically shadowing the clinicians there. And at the end of the day, so the patient sees many different doctors over the whole day, undergoes a battery of different tests. And then at the end of the day, the clinical team comes together with the patient. They're all sitting in a room. There's probably something like 20 members of the clinical team. And there's the patient and his family. And in one particular case, it was a patient who didn't speak English as their first language. So there's also a translator. And the clinical team was trying to explain, or was successfully explaining through the translator, that this patient had a progressive neurodegenerative disease that affects their personality. So this person was showing symptoms of aggression and kind of inappropriate behavior that happens with some degenerative disease.
Can you describe, what is a neurodegenerative disease?
So that's a disease that ultimately kills brain cells.
Okay.
Long before brain cells are killed, though, there's a lot of other damage along the way.
Okay.
So it's degenerative because it's causing irreversible damage.
Okay. And it's going slowly along the way, and it's almost like chipping at something and in those cells so that the cells can no longer function in the way they would normally function. Neuro being brain, then, in this instance.
Exactly. Yes.
Okay. So in this particular patient, and we see this also, I think about this with traumatic brain injuries. When we talk about football players and athletes that have challenges with that later, that then their personality is changed. So then you hear of these stories of aggression and some things that have happened out in society. And it's really sad to see, because the individual, you think, oh, this looks like the same individual. Why are they behaving in this aggressive manner? Which for family members is really hard to deal with.
That's exactly it. So this family, even though they were being told that their patriarch was suffering from a disease that was incurable, in some ways they were relieved to discover it was a brain disease, not that this person that they loved had basically become a jerk.
Right.
Yeah. And that's exactly the issues. The person looks whole, but they're not. They're not whole. They are suffering from a severe illness. Okay,
so you're back in this area, right? And you're talking with this family. And I also can picture the environment, like all these different clinicians in, and that's a highly stressful, and it's a really delicate situation talking to the patient. So how did that translate into you becoming passionate about the work?
Yeah, so in that shadowing of what was happening at the clinical level, it became really obvious to me that there's a huge gap in terms of the tools that we have for neurodegenerative diseases broadly. At that time, there were very few drugs. There are some more now, but they're still not that great. And our diagnostic tools aren't that great either. So there's just a huge opportunity as far as being able to do science that would be impactful. If we could even move the needle a little bit, that would be a huge impact.
Right. And for diagnostic tools, I think that's also a struggle for families, right? Because Alzheimer's slowly comes on and you start seeing other things you can't tie to. There's no distinct immediate test to say, oh, this person is going down the path for Alzheimer's. So the patients that they get to that stage, they've gone through a lot and their families have already gone through a lot, which is such an emotional journey. I love this. And I think so much of the world can think of famous people that they know that have passed from Alzheimer's. And so it's a really big struggle. So thank you for digging into that. Yes.
Can I add one thing to the diagnosis part of it? So by the time we diagnose the disease, it's probably been going on for 20 or 30 years.
Wow.
So it takes that long for something like memory impairment to become apparent. And that's part of the problem. We need to be diagnosing it much earlier before all that damage has happened.
So we think about this a lot, for example, cancer, okay? Mm-hmm. And why we tell people, women, right, to go and be tested for, because the earlier you detect it, the better chances of survival. And I think in this instance, perhaps the earlier we detect it, the better livelihood that the individuals are going to have, the more opportunities you have to really change the impact on this family's lives, which is just significant. 20 or 30 years. Wow. Okay. I'm blown by that. Okay, so talking about your research, Let's talk about a little bit about the funding of research, okay? Because I think that's one of the things that we struggle out in society if we're not doing research is understanding, why is this drug so expensive? Why is this treatment so expensive? Why is my hospital bill so expensive? And it's a struggle that as scientists, we would love for it to be as available to everyone as possible. So can you tell me a little bit about the journey, a brief about the journey of a treatment such as yours and how you get the funding to be able to actually do this important work?
Yes. Okay. So there's a lot of parts there. First, the journey. It starts often with lab research in a cell culture system or in animal models.
What do you mean? Like, what's an animal model? An example?
A mouse that has been genetically changed to express the pathology of Alzheimer's. So you've probably heard of plaques in Alzheimer's. Those are these things that are basically proteins that bunch up and are a hallmark of the disease. We can express those in mice.
So basically we take mice and we're able to modify their genes so that they then behave with the same characteristics as a human that has that disease, which is a science in and of itself. It's amazing that that's ever been able to happen.
Yes.
Okay, so it starts in a lab where you've modified, you've allowed these mice to have the characteristics that we're looking for. So in this instance, memory loss or something of that nature. And then you utilize the cells of those to test the cells in the cell lab.
So for us, we'll utilize the animal trying to understand something like memory impairment. We'll record from neural activity during a memory task, and then we'll do this kind of stimulation that we're testing if it's going to be efficacious or useful in the disease. So we'll do that first in mice. We'll see if it, for example, improves their memory, if it reduces some of these markers that we use of the disease. And then if it works in mice, then we consider how can we take it to humans. Our first foray into stimulation was a technology that we knew would be hard to translate into humans, that optogenetics. But then through some trial and error, we figured out we could do it via sensory stimulation, that lights and sounds that flicker on and off. And then I was like, oh, well, this is very testable in humans. And so for us, I then went to Alan Levy, who's the head of the Emory Brain Health Center, and I said, here's where we are with the basic science, and what would it take for us to test this in humans? Honestly, I thought he was going to say, here's 5 to 10 more years of basic research, lab research you need to do. But instead he said, let's do it. Let me introduce you to some people. And he introduced me to other clinicians and staff members at the Emory Brain Health Center. And we started talking about how do we turn this into a clinical trial. And that first clinical trial is what we call a feasibility trial. So it's safety. Basically, whether people will tolerate it, whether people will do it. Because our stimulation was an hour a day, every day.
I've toured your lab. I believe it was for one of the College of Engineering board meetings. I toured your lab and I saw the mice and the different time points and the different interactions that they had and then how you tested them, I believe in a maze or a game or something like that. It was so fascinating. And so I think one thing that you just said right now is really, really important. So I'm teaching a master's class at Emory and I'm talking to the students about you can come up with a great idea and a great solution, but if the patient will not do that treatment, if the side effects, the time commitment, the pain allotted with it, then it means nothing. So I love that early on you're thinking, wait, are these patients going to sit for an hour a day?
Exactly. And the clinical team was like, no, they're not going to do it. They're like, no way. I mean, sure, we'll try it, but it's not going to happen. So that was our first study. And in fact, actually the safety and the feasibility, were very high. People did it and they did it reliably and they what we call tolerated it well. It's not that they loved it, but they didn't say, oh, this is awful and I'm never going to do it again.
I mean, we can't get people to exercise. I can't exercise for an hour a day. But this is exercising your brain in a way for an hour a day in these type of conditions, which is a lot. Now for a feasibility study, so a study that says, is this possible? And is it safe? It's not going to cause huge difficulties or challenges for them. How many patients did you have to enroll?
Yeah, that was 10 subjects, which is a very small study.
Yes.
But is appropriate at that early stage.
Yep, absolutely. Okay, so that was successful. They did do that. And then what came next for you?
So after that, we did another study about mechanisms. But the next step really from what we call a feasibility trial or that early trial is what we call a phase 2 trial, slightly larger, slightly longer, and then a pivotal trial. Cognito is a company that is actually doing those trials. The phase 2 trial is done. They've had some positive outcomes. And the phase 3 trial or the pivotal trial is currently underway.
So the phase 2 trial is really trying to say, so first you say, okay, can we possibly do it? Will the patient be willing to do it? Mm-hmm. And is it safe? Mm-hmm. And then the next trial is, okay, not only now we've determined this, now we have to go in and determine, are we seeing any sort of positive impact from it in a next size population? And then the pivotal trial is really the trial where you have a large population. You make sure that it's diverse in the cultures of the individuals, where they live, their ages, all male, female, all that kind of stuff, to then say how broad is the success of this in the general population. And you're right now about to start the phase 3?
Phase 3 trial or pivotal trial is underway.
Oh, amazing. Okay.
Yeah.
So now let's get back to funding.
Yes.
Because I want to say the reality of it is, in order to get to the point where we're testing patients who could potentially have Alzheimer's way ahead so that we can have the improvement, we have to start with this basic science and all these trials. So where do you get the funding for that?
Yes. So the lab research that I talked about, that's been funded by the NIH. There have been some foundations that have been really crucial to our next lab research step. So, for example, we're now working on using this stimulation at earlier stages before you might see memory impairment, or to mitigate or reduce the risk of developing the disease. That's been funded by that because that was a high risk project that was initially funded by a foundation called Bright Focus Foundation. But largely our funding has come from the NIH. Those are just much longer, larger grants, so you can do a lot more research with them. And then as far as getting into the trials, trials are really expensive. Especially the bigger, the longer it is. So typically that would be funded by industry. There's some NIH funding for that, but making that leap to something like a pivotal trial, that requires industry, which means for something like a startup company, that would be venture investors that are funding that. For a larger company, that would be part of their R&D or research and development budget.
Yep. So National Institutes of Health, which really is so critical for so much of the research that we do, is that they have the funding to be able to then support the work that you're doing so that it eventually gets to the patients and also to the families of all those patients. Because as you mentioned, the patriarch, the head of the family, is now dealing with it. So it impacts every single person along that chain. That is really amazing. Okay, so let's go to here. Beyond the science, how does your lab impact the community? So when you're thinking about jobs that are offered, maybe training to the community and healthcare in general.
Yeah, absolutely. We are an employer, right? Those NIH funds, they pay for both students who are undergoing training, but also staff members. And not just staff in my lab, but the staff that basically makes all of the research facilities, the buildings run, everything on campus. So that is we're a huge employer.
And especially in your research, it also helps to fund the animal labs and the people who take care of.
Exactly.
Because I think most of the world doesn't understand that animals that are utilized in research are really, the people who care for them are really focused on giving them the best quality care that they possibly can. And that takes a lot more time, money, and energy than a lot of people would understand of that piece of it. So I think it's also those things when I think about, I know when I look at budgets and then I remember, oh, wait, we actually have to have the lights on and we actually have to do these things. So
yeah, we're paying for the staff for the animal facility, but also for what we call the microscopy core, where the microscopes are. There are other sort of shared facilities among labs that have staff who make those places run. So So yes, it's not just the people who work on the particular research problem.
Yeah. That's amazing. And it's so complex. So, okay, let's dig in. Who's on your team and why do you need such different backgrounds to make discoveries?
Yeah, that's a great question. So I have a mix of students who some might come from a biology background or a neuroscience background. Some come from an engineering background or a math background. I'm trying to think if there's anything farther afield than those, but that's probably a pretty good summary. And the reason why it's useful to have such a good mix is because our research is ultimately really interdisciplinary.
It is.
So people have to be able to code. They have to be able to do the math and be comfortable with it. They have to be able to understand the underlying biology and the nervous system, and they have to put all those things together. We build a lot of things custom in our lab. So we have people in the lab who are really good at basically building hardware, 3D printing, wiring things up, all that stuff. All those skills are required to make it work.
What do you have to code? So code is in like building a computer program.
Yes, right. So all of our data is complicated, and to analyze it requires writing code. Because, for example, in one experiment, maybe we recorded hundreds of neurons, and it's not just hundreds. It's actually we record them every millisecond.
Wow.
For hours. So we just
have all this data.
Massive data.
And if you were just sitting there with a calculator, that would not work. So someone then writes a program, like software, that then you put all this data in, and magical analysis comes out and tells you, are we seeing something that's potentially beneficial or not?
Yes, it's like that, but not exactly magical, more like blood, sweat, and tears.
There we go. I love that. Okay. So where have your students or trainees gone on after working with you to make a difference in the world?
Yeah, great question. So a variety of different places. One, for example, was an MD PhD student. He's now doing his next step in medical training. He's going to become a neurosurgeon. One is at the NIH working as a scientist there. One is at a government lab called LBL, Lawrence Berkeley Livermore, working as a data scientist there. One's doing a postdoc, which is another research position. One of my former trainees started her own business as a consultant, and she uses her neurotraining to train business leaders. And another one is doing science writing.
Oh, you know the thing I love about thinking about that? So you have the MD PhD. So this is someone who really wants to go to school for a long time because they're going to be a medical doctor and they're going to be a PhD. So they're going to have a doctor in some sort of research. And then he's going to go and be a neurosurgeon. So bless his heart. So you have that type of industry, and then you have someone who's doing consulting and helping leaders based on the brain knowledge, the neuro knowledge that she learned. She learned working in your lab. And I love the just how much this science and learning these skills can really be translated into every part of the world.
Exactly. And I really encourage my trainees to pursue all kinds of different avenues. Some of them are really interested in things like entrepreneurship, and I'm all for it. Go find interesting, exciting problems and solve them, whatever capacity that's in.
Yeah, that's amazing. Well, I'm a big fan of entrepreneurship since I run commercialization here. So there you go.
Yeah.
Okay, so what role... I'm going to skip that one because we've already dug into this. And I want to know more about you as a human being. Sure. So we're going to dig into this, okay? So we talked about what pulled you into the Alzheimer's research that you are doing. But what pulled you into just biomedical engineering or engineering in the first place? Was there a moment or a story that really you said, oh, this is what I want to do?
Yeah. So I think even before I started my PhD, I wanted to use neuroscience to improve human health. And I actually did my PhD in neuroscience, not in biomedical engineering.
We'll forgive you.
Yeah. But when I was doing my PhD, I was always trying to use new cutting edge tools, and I ran into a whole host of problems. There's a whole slew of failed projects that I left behind. Luckily, I had, enough things worked for me that I got my PhD. But one of the things that I learned was, well, if I want to be using those new tools, or if I want to be pioneering new tools, I really need to get into the engineering of it. So I did my postdoc, or after the PhD, in a neuroengineering lab. And that was when I just got to really delve into the engineering side of it, and invent whatever tools that we felt like would be useful to tackle the problem.
Okay, when you were a little girl, what did you want to be when you grew up?
I wanted to go into technical theater, actually.
What is that?
So that's like sets and light design and things like that. So the first circuits I built were actually for lighting for the theater.
Do you find it curious that you're now using lighting and sound in your research so many years later?
Yeah, I find it really curious. I think it's probably not a coincidence.
Right? Yeah, no, I love that. I'm glad I asked that question. Okay. So outside of the lab, what keeps you grounded? Do you have any hobbies or passions that balance off that science brain of yours?
Yeah. I mean, I walk a lot or hike, things like that. That helps me just to be outside, to be moving. It helps me center myself. I also spend a lot of time with my kids. So, whether it's going to cross-country meet or going camping with the Cub Scouts, I'm out there hanging out with them.
You know, the thing I love about the walking outdoors part, when you were talking about the sensory impact earlier, is that when you're outside in nature, that the grounding piece of it, really it's the wind on your face, it's the sounds, it's the light depending on the day, it's everything you see in nature. So thinking about the way that those sensory things impact you and ground you, I can see how that sensory and the light component could have an impact on those circuits in the brain.
Yes, absolutely. And there's multiple studies that have shown basically being in nature is good for your brain, for your mental health, for your stress levels, etc.
Okay. I love how these things all tie together.
Yeah.
Okay. When progress feels painfully slow, what keeps you pushing forward?
Yeah. I think a couple things. One is it's really helpful to have a life outside of work. Sometimes you just have to disconnect from the stress of the research. The research really is a roller coaster. Sometimes you think you're onto something awesome, and then takes a turn, and suddenly everything you thought was true is now wrong. You've wasted months and maybe years, and it feels really painful. So you have to be able to weather the ups and downs. So life outside of the research is a big one. I think is helpful is to have a couple different things going at once, different projects. Some will be up and some will be down, and having different projects helps balance those out.
I love that. Have you heard what Thomas Edison said when his lab burned down? I think about this all the time when I'm working with entrepreneurs and scientists. Is he said, "Oh, thank goodness, all of our mistakes have burned down." It was something like that. I think we forget how many times we have to work towards something to actually find those pivotal moments, which is really critical. Okay. If you could give the public one simple thing to say when advocating for research such as yours, what would you suggest?
I think that to make the really big breakthroughs, we need to fund basic research. A lot of the things that ultimately led to the most impactful technology were based on initial discoveries that it wasn't clear how they would be applied, but they became huge later.
Yeah, I love that piece. Okay, in one sentence, why should the average person care about biomedical engineering?
I mean, we're going to improve human health. That's what our goal is, not just me, but really the field as a whole.
When you look at the work that you've done thus far, which piece of it are you most proud of?
There's so many. I think I'm really excited about how we've been bridging across disciplines. Or taking a new perspective on disciplines. So, for example, with the brain stimulation for Alzheimer's that I mentioned, the field really had been focused on drug development, and it still is, but we're trying to take a new perspective. And we've done that in other ways as well. I think that is a key part of how we've been inventive.
You know, I love that you highlighted that because I see when we think of interdisciplinary, so it means people from different backgrounds collaborating together. The thing I love the most about that is you do get those where someone comes in with a very different viewpoint and says, hey, wait, what if we tried this? And it's so critical to be able to advance this. Okay, so what are you looking forward to in the next couple of years?
Good question. We have a couple things cooking in the lab that I'm excited about, but I'm also excited for us to start some new directions. Some of the things that we're looking at is trying to use stimulation in earlier stages. So I mentioned we need to detect Alzheimer's earlier, but we also need to intervene earlier. As the field gets better at the detection earlier, we need tools that can intervene early too. So we're looking at some of those options.
Okay, and going back to what the light and the work that you're doing right now, what do you envision the outcome? So when you're talking about in your phase 2 trial, which is the trial you're really trying to see, does this make an improvement? What are you envisioning that improvement to be?
So first of all, it's not my phase 2 trial. That's Cognito ran that. But in that trial, they saw, so first let me just back up and explain. In Alzheimer's disease, an outcome that you would expect is to slow decline. You're never expecting a rescue of function. That's because we're intervening.
It's not
late.
a cure, but it gives them a better quality of life for a longer period of time, potentially.
Or if the decline is going like this, it steadies it out, right? That would be, that's what we're hoping for in a therapy.
Okay.
Not that it's going to improve things, right? That's just the state of the art right now. Again, because we're intervening relatively late.
Yep.
So they saw slower decline in brain volume and in some memory measures. So that was great news, but still, not the big trial. And I'm looking forward to seeing the outcome of the big trial.
Amazing. So how, if individuals are interested in following your research, how can they follow your lab or follow the work that you're doing?
Yeah, so we have a lab website, singer.gatech.edu. They can check that out.
And we will put that in the show notes.
Excellent. I also post on LinkedIn when we have new papers come out and things like that.
Yeah, so definitely follow you on LinkedIn, follow your website, and continue to follow the podcast because if she has something advancing that's amazing, we're going to share at some point in the future. So thank you so much for coming here today. We're really grateful.
Thank you for having me.
That's it for this episode of Holy Shift, Biomedical Breakthroughs Shaping Tomorrow. If today's conversation sparked your curiosity, pass it along to someone eager to explore the power of research to change lives. As a reminder, the opinions expressed in this podcast are those of the host and guest and do not represent those of any organization mentioned. Be sure to follow or subscribe wherever you get your podcasts so you never miss an episode. To learn more about the research featured on this show, visit bme.gatech.edu or check the show notes for links and resources. Thanks for listening, and remember, behind every innovation is a purpose, a person, and a powerful story.